All right, so this example problem adds a little extra, a couple layers of complexity compared to the ones we've been doing so far. And this one will help you as you try to work on question number 3 from worksheet 2 and question number 6 from worksheet 2. Question number 4, we're going to kind of do in class together today. And even question number 3, we're going to have you try it on your own, but then we'll check it in class. So by the time we're done today, we'll have used this as sort of the foundation. And then you'll try number 3, we'll check it. You'll try number 4, we'll check it. And then we'll probably start number 6, and then that'll be what I want you to try to finish for our next class. So that's the goal, kind of the outline. So those of you that might be watching the video, I'm just going to record this example that we're going to go through detail by detail. Hopefully it helps lay the foundation for you to solve those other ones on your own, but you can also come in and meet with me during lunch or after school to get some help with that if you need. All right, so this one, we've got 2 vertical walls separated by a distance of 1.5 meters as the diagram shows. A uniform board is propped between them. Wall 1, the one on the left, is smooth enough that the wall exerts a negligible friction force on the board. Wall 2, however, is not smooth. It has a coefficient of friction between the board and the wall that is 0.98. It's actually a reasonably high coefficient of friction. What is the length of the longest board that can be propped between the walls? So if you think about this practically, what has to be true about the length of the board?
Longer than 1.5.
Has to be longer than 1.5 for it to touch both walls, right? And if it's too long, if you can kind of imagine it, the longer it gets, the steeper that angle gets, right? And so the steeper that angle gets, the harder it's going to be for the friction on one side to hold it up. Right, so we want it, it's probably going to be a fairly shallow angle. It's not going to be like an 80-degree angle or something. Otherwise, it would just fall. The friction wouldn't be strong enough. So our goal here is to try to figure out, knowing a little bit about the friction and knowing that because we've got a lever arm here with some forces acting on it, we've got torque, what is that angle where the board would have enough friction that it could pin in there and not slide down? Okay, so can't be too long, has to be more than 1.5 meters. That's the goal. So let me get you the zoomed in picture here, and let's start drawing some forces and thinking through some torque values. So what are some forces that we could evaluate here that might help us solve this one?
Friction force.
It's going to be the friction force, and where are we going to draw that?
On wall 2.
Okay, so on wall 2, this board meets wall 2, and there's going to be an upward friction force trying to resist the gravitational force pulling it down, right?
Mm-hmm.
All right, there's one force. What else?
We're going to want to know the normal force and the gravitational force.
Good. And one reason we need the normal force, I mean, obviously it exists, but yeah, like you were saying there, the friction force is based on the coefficient times the normal force. So we're going to need the normal force. And this one, we'll just call normal force 2, since it's on wall 2. But if that wall's pushing, then this wall also would be pushing. There's no friction over here on this one, but there would be a normal force. So we've got normal force 1. Just since it's wall 1, we'll just distinguish it that way.
Now in this case, however, would the gravitational force be equal to the normal forces or the friction force? Or none of the above?
Well, where would the gravitational force be? How would I draw that on this diagram?
Center of mass.
Yeah, from the center of mass. And what would its direction be?
Down.
Straight down. So there's this roughly the center of mass. I've got this gravitational weight force. I'm just going to call it FB for board. It's the weight of the board. And so it's perpendicular to the normal forces. So would it be balancing the normal forces at all? No, it's vertical, they're horizontal. So it's balancing
The friction force.
friction force,
So
or
since there's only
the
one
friction force is balancing it.
That means that the friction force of wall 2 will be equal to the weight force of the board.
Good. So the friction force is going to be equal to the weight of the board. That's one equation we know, because those are the only 2 vertical forces. So they must be balanced in order for the board not to slide down, right?
Also, would the torque be equal on each side because it's not like rotating or anything?
Yeah, we want it to be propped in there, so we're also gonna be able to come to the torque. We'll get to that in just a second, and we'll actually set up that equality. Before we do that though, what about the normal forces? Are they equal?
I don't know.
Yeah.
How do we know? Yeah, they're both perpendicular to the wall, so they're both horizontal. How do we know that they have to be equal?
Inverse opposite angle.
For the angles, that will help, but in terms of the forces, somebody said it, I think.
They aren't moving.
Yeah, the board doesn't go side to side, so they must be balancing, otherwise the board would accelerate right or left. And since the board isn't moving, we know that those two forces have to be balanced as well. All right. So we've got our forces figured out. There weren't too many, but a few. We've figured out which ones would balance which ones, because if it's just propped in there, nothing's moving, no accelerations, so we should see some equivalencies. But we don't really know any numbers except for the coefficient of friction, right? So we know this coefficient of friction. Let me redraw that, it looks a little funky. We know that coefficient of friction, and bless you. We know the board has to be longer than 1.5, but we really don't know enough to solve anything yet, so we're going to need some additional equations. And Aaron got us off on the right track there. Or, he's saying, hey, what about the torques? The torques have to be balanced too, otherwise it will rotate. Well, to figure out the torque equations, we have to pick a pivot point. So there isn't actually a pivot point here, right? There's no hinge, there's no pin.
But could we not think of the friction force acting kind of like a hinge?
Kind of, yeah. We could pick that point if we want. We could also pick the middle of the board. We could also pick the other side. The friction force kind of makes sense though to me too. Like it's almost like it's stopping it a little bit there. So it kind of makes sense. Can you think of any mathematical kind of strategy why choosing that position might be helpful?
Well, let's see, looking at remind me what the torque equation is again?
The torque equation generally is the force times the distance times the sine of the angle. Oh, I'm not sure why that, there we go.
Well, what's nice, the problem with having it in the center of the board is it's gonna be more difficult to get an angle.
Okay,
For the distance, well, I mean, if you have it at either end, you're gonna be able to, just have the entire length of the board instead of having to worry about, 1/5 or what have you, like we did yesterday.
Mhm.
And then for the force part of it, I'm assuming if we were to use the normal force, we may need to consider the normal force of both sides, whereas with friction force, we can just consider friction force and that's it.
okay.
There's one number.
All right, so there's a couple thoughts. Quinn, were you gonna say something different?
I was just gonna say it's easier to like solve for side lengths.
For what?
Side lengths.
The lengths. Okay,
Yeah,
good.
using, like,
Yep. So you had some similar thoughts there. Here's another reason, or does anybody have any other thoughts? I have one, all those are good, but there's one more that I'm not sure if anyone's thought of yet, and I want to introduce it because it could help you in other scenarios. Anybody have another reason why mathematically it's kind of advantageous to pick this spot as our pivot point? All right, so here is our equation. If I choose that as the pivot point, how far is the friction force from there?
It's right there.
Zero distance, right? That means it's giving zero torque. How about the normal force?
It's right there.
Zero distance, so zero torque. So in my torque equation, I've just eliminated two forces from consideration. Now I only have two forces that could be causing torque if that's my pivot point. So instead of putting it here where I'd still have three of them to consider, or here where I'd still have three of them to consider, if I put it there, I've only got two. And since there isn't an actual hinge or a true pivot point, we can pick it wherever we want, and conceptually, like you were saying, Alex, kind of makes sense. That's where it's gripping, but mathematically, it trims things down a bit for me. It gets rid of two forces in terms of my torque relationship. Okay, does that make sense? And so often a strategy, if there isn't a true hinge or something, then I would say, think about that a little bit, see if you can simplify the problem for yourself in terms of torque. It doesn't simplify the forces. The forces all still exist. It's just a matter of those two wouldn't be causing any torque if that's my pivot point. All right, so if this is the pivot point, then the weight would be trying to pull it this way, right, in the counterclockwise direction. And the normal force is not letting it, so it's creating a torque this way. Now, it obviously wouldn't move the board that way, but that's the direction because it has to oppose this. Does that make sense? The wall isn't actually going to push it, but gravity's trying to pull it this way, so the wall is saying, no, I'm going to create an opposite torque to cancel you out, okay, and keep it balanced. And since it's not moving, we know those torques have to be balanced. So if I go to my torque relationships, then I could say the torque caused by the weight of the board has to be equal to the torque of that normal force created by the wall. They're fighting each other to keep the board from rotating. So we okay on our force relationships and our torque relationships so far? Is it clicking all right? Any questions before we start actually substituting some other things in? All right. So
Well,
we
actually,
yeah, go ahead.
So for the reason why we're using the torque of normal force 1 to determine the torque of the board is because it is the least complex.
Well, these are kind of canceled out because of how we chose our pivot point. And the board is trying to rotate like this if it really is fixed there because of the weight.
Mhm.
So that means this must be providing a torque that's opposite that.
Mhm.
So that's the only other, because a torque can only be caused by a force. And so the only other force that's not at the pivot point is that one. And so that, and we can kind of see too, that's what's keeping the board from falling. So it's trying to fall because of the weight, but the wall's saying no.
Okay.
All right. Anything else? All right, well, we've said that torque generically is just the force times the distance times the sine of the angle that that force makes with the lever arm. So let's go ahead and start plugging a few things in. For the board, the force is just the board's weight. So since I called it FB up above, I'll just call it FB here. And how far is that from the pivot point?
1/2 bar? Wait, which one?
The weight.
1/2 bar.
Yeah, 1/2 R, 1/2 L, whatever letter you want to use for the length of the board. I've got a bunch of stuff already written down here, and I used L, so I'm just going to say its distance is 1/2 L, because it would be right in the middle of the board is where the weight would be effective. And then I don't really know any of the angles, right? They didn't tell me the angle. In fact, we were saying earlier, we kind of have to figure out what that angle is so that it's not so steep it slides. It's going to be probably a relatively shallow angle. We've got to figure that out. So I don't know what it is, but I do know that I'm going to have to think about it because that force is not perpendicular to the board, right? There has to be an angle there. And so you draw this, whatever that angle is, I need it to finish out that part of the equation, right? You okay with that? So that is just the torque of the board, the board's force, where that force is, and what angle it makes with the board. All right, so how about the normal force? How is this torque equation going to look? Well, let me go back to our blue here.
Well, it's gonna have. Now, is it gonna have the same angle, or is it going to have the opposite angle, the supplementary angle?
Complementary?
Complementary, sorry.
Yeah. Well, it will for sure be complementary. They could be equal if it happens to be 45, but most likely not.
Yeah.
So it will be some different angle, but it will be complementary. Yeah, Quinn?
Isn't it just 90 degrees more, so like the cosine of that theta?
Yeah, so we're gonna get there in just a second.
Okay.
Yeah, but yeah, it's gonna be, if I just start plugging in the basics here, we've got the normal force, that's the force that would cause the torque, right? We're talking about the torque caused by that, so that's the force. And then what's its distance from the pivot point? The whole length, right? Just L, since that's the letter I chose. all right? And then sine of, now, just to keep it simple for now, I'm just gonna call this sine 1, and then this is gonna be sine angle 2, because chances are they're not equal, but we know that they are complementary. And so that's gonna get us back to what Quinn was saying. There is a relationship, and I don't remember the exact way you see it in the theorems and postulates and such, but basically the idea is if I have the sine of an angle, that's going to be equal to the cosine of 90 minus that angle. It's complement, right? Is that ringing a bell from some of your, something like that? I don't know if that's how it typically looks in the textbook, but you recall that kind of relationship where we've got the sine cosine relationship for the complementary angles in a triangle? So we're going to capitalize on that because we know that they are complementary. Now, that may not be totally clear why they're complementary. So let's take a look at the geometry just a little bit more. So on the next slide, I've kind of cleaned all this up a bit and made it a little bit neater. This is sort of our workspace, but here we've kind of trimmed it up a little bit. So I just put my forces over here, and I've taken away the torque equation just for a minute, but if this is the normal force making this angle, do you see how this is like a Z, right? So that means this and this are opposite internal angles, right? Right, seeing that? We go boom, 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 so these two have to be equal. And then you see how this makes a triangle? That means these have to be complementary because this is straight down and this is straight over, so that's a 90-degree triangle. So those two have to add to 90. Be okay with that? Is that tracking all right? I can draw that out if that's helpful, or do you think it's clear?
Don't they subtract to 90?
Well, 90, they would add up to 90, right? Because all three of them in the triangle have to be 180. So since this is 90, those two have to add up to 90.
Oh, I get that, yeah.
See what I mean? Okay, so hopefully that helps with the geometry. Any questions on that though before we move on? All right. So now let's expand that a bit. Let me scroll it up a little so you can. I don't think we need to see the question anymore. We kind of know that, plus it's on your paper. So we've got this figure here, we've got these forces here, and we've got this relationship, right? We've got the board's force or weight times half the length times sine of whatever that angle is. I just made a different symbol, phi. I could have done theta 1, theta 2. I could have done theta and 90 minus theta. I could write it however I want. I could do theta and cucumber, like whatever. I'm just using a variable, right? I can make it whatever I want. So, but I know they're complementary. And then the other normal times length times sine of the theta angle that's the same for both normal forces. All right. So then that principle that Quinn was mentioning, that those complementary angles, if I have the sine of one of the angles, the other one is going to be the cosine of that same angle, right? That's the relationship. So since I know they're complementary, I just change the sine of that complementary angle to cosine of the original angle, since they are the two complementary angles inside that triangle. So whichever way you learned it in your math class, whether it's more along the lines of this sort of relationship, or whether you've learned it some other way. Haven't taught that level of math in this school, so I'm not exactly sure what the curriculum here is and how they define that. But whichever way you understand that complementary angle relationship, that's what we're using here. All right, so questions on what we've developed so far? That's the hard part. Okay, that's the hard part. So if you followed so far, then you're in great shape. The rest is pretty much just algebra with a little trick, but not too much. Okay, so I want to make sure you get this well before we get onto the algebra. I think you'll get the algebra fine. But I just wanna make sure there's no confusion here. You okay? Any questions at all? All right, so looking at the algebra now, can you see some things that might cancel or some things we might combine to simplify a bit? Even without doing any substitution, just looking at what's just there.
Tangent.
Sorry,
You can make a tangent.
how's that, Gilbert?
It's like if you move, I guess you can make a tangent or cotangent by moving sine or cosine
To the same
to
side?
right, yeah, right.
Yeah, so if I just move cosine over to this side, it would be sine theta divided by cosine theta. And
Why
that's
don't
just
you
gonna be tangent.
Well, why don't you just get cotangent, therefore.
I could do that too.
more simplified, because then you just have to divide once more by the normal force of, well, one, then you get your L.
Well,
Whereas-
would the L's cancel?
Yeah, well, they'll cancel, but aren't, yeah.
If I divide this side by L, that cancels. If I divide this by L, that cancels. So so the L's cancel each other, right?
Mhm.
So whether we want to go cotangent, tangent, up to you, whatever you prefer. The L's cancel. I can combine the two angles in my functions, sine and cosine, to make the tangent. So now I'm not going to have two of them. It'll simplify to one, right? So that's kind of the step we're going to take here. Just put the sine and cosine together on one side, put everything else on the other side. The L's cancel. The sine over cosine is going to become tangent. And so when I simplify that a bit further, I just have the 1/2 times the weight of the board divided by the normal force equals tangent of theta. So once we get the torque situation figured out, then it's just kind of, okay, can I simplify this? Can I cancel anything? Can I combine some things? It's really just algebraic reasoning at this point, mostly. But I'm not done yet, all right? But I do have an equation now where there's only one angle. And remember, that's what we said we needed to find is, well, what angle will that board stay? And we've set this up to say, well, it would stay if the torques were equal. And if the torques are equal, this is the equation that tells me the angle, right? That's how we built this scenario. And so if we can figure out how to solve for theta, we know the angle. Well, any ideas on where I could go from here? You got an idea, Quinn?
But if you set the, wait, never mind.
It's like
Wait,
that
to solve.
equation.
You got an idea, Michelle?
To solve for theta.
Yeah, what I might be able to do so I can actually get a number? Sorry?
Use the tan inverse and then multiply by 1/2.
Yeah, I'm gonna use the inverse tangent function of those other values. Do I know FB yet?
Yeah, like FB is like the coefficient times like Fn2, but Fn2 is the same as Fn1.
Okay, good. So these other forces I had over here, like FB we said was friction or equal to friction, and F1 we said was actually equal to Fn2. Ashley, were you gonna say anything different or
Yeah, I was just gonna say pretty much the
same
same thing.
thing?
It's gonna be like FB is just gonna be the coefficient of friction times
Good, good. And we could either, and I did it one way, she said it a different way, both are exactly correct. So she just made coefficient times Fn1 so that the Fn1s would cancel. I just changed the Fn1 to Fn2. Doesn't matter, they're equal, so whichever way you want to substitute them. Because Fn1 and Fn2 we said were both equal to each other. So when I just substitute those forces back in, suddenly, whether I substitute Fn1 or Fn2, whichever way I do it, what happens? Those forces cancel and I'm left with what?
1/2 coefficient.
Yeah, 1/2 the coefficient. And they gave us the coefficient, right? So we can just plug that in and then do what Michelle said, just use the inverse tangent function and that'll give me the angle. Give you a few seconds to plug that data in and see if you come up with the angle. About 26, is that one here?
Yeah.
All right, very good, that's what I got too. So what does that 26 degrees mean in the context of this question?
Now know the angle.
We now know the angle, and what's that angle for? Just make sure we haven't lost track of what we're doing here. What angle is that even measuring?
The torque equation.
It's compared to the torque equation, where the torques would be balanced. Even more practically, like, what does that tell me about the board?
Like the angle it makes with the wall, like at whatever length it is.
Yeah, so that angle that it makes here with the horizontal, because that's the angle we measured as theta, right?
Oh, you can solve for the length of the board now, right?
Yeah, now we know what angle that has to be at. Now, it could be less than that angle, but the question said, what's the longest the board could possibly be? So if it gets more than 26, it's too steep and it's gonna slip. But anything 26 or less will work. So 26 would be like the biggest angle possible where the torques still stay balanced and the board won't slip. So since we know the angle, now like Bennett was saying, we can figure out, well, if the angle's 26, I can calculate the hypotenuse basically. So here is what that looks like, just in green down here. I know the walls are 1.5 meters apart. I know the angle the board makes is 26 degrees. And so I can just use trig and figure out how long that board is when it makes a 26 degree angle.
Can I charge my calculator?
No, you're not. How dare you? Alex, keep all the shots down.
Now, does the value make sense? We got 1.7 meters. Is that logical? Yeah, it's longer than 1.5. It has to be at least that long, right? And that's a pretty shallow angle. It's just a little bit longer. So pretty shallow angle. So it makes sense it would lodge in there and get stuck. If it was much longer, too steep, this slip right through.
Now, does that work as our maximum length?
So if it were shorter than that, so anywhere between 1.5 and 1.7 would work. So if it's 1.51, it's just long enough that it could catch and stick.
But it said what's the longest length?
So that's the
Did it
1.7.
specify at the angle it is at?
Well, what we try to figure out is what angle would the torques be balanced? And so now we know that like, if we get above 26, the torque won't be balanced anymore. And so we know that the longest the board could be would be at an angle of 26. If it's shorter than that, as long as it's still more than 1.5, if it's shorter than that, that's still gonna be fine. But if it gets longer than that, the angle gets too steep, it'll slip, it won't go, because then the torque won't be balanced anymore. All right, how are you feeling about this one? Tracking okay with it? I have to tell you, you guys seem the most confident of all 4 classes. A lot of the other classes are like feeling pretty overwhelmed by this, but you guys just seem pretty confident and calm, cool, collected. I hope that's a good sign.
Cool as a
Seam?
cucumber.
Seem? It might not be actual, huh? All right, so any questions before I have you try a similar one on your own?
Oh gosh.
Everybody feeling okay about this one? Yeah. All right, so if you look at worksheet 2, question 3, it's pretty similar. We got a uniform board leaning against a smooth vertical wall that's frictionless. So we had a frictionless wall in the last one. The board is at an angle. Okay, we had a board at an angle last time. It says there's a coefficient of friction between the ground and the board. So instead of between a second wall, now it's against the ground, but there's a friction coefficient. And they want to find out what's the smallest angle that a lower end of the board does not slide along the ground. So the idea here is like, say you have your surfboard and you want to lean it against the wall. Well, if I lean it against the wall and it's too angled, it's just going to slip, right? And they want to know, well, how steep do I need to make that surfboard so it doesn't slide across the floor if the coefficient is this amount? All right, so that's the basic premise. So you're going to use a lot of the same things. I would suggest draw a picture, put your forces and torques together and see what you can come up with. Every few minutes, I'll just pop up a little bit of my work so you can kind of compare and see. You don't have to necessarily do it the same way I do it, but at least you can kind of compare and see if you're coming up with something similar.
Is there a pencil sharpener?
The only one that I know of is on the shelf down by that red door by the sinks. And I'll go ahead and stop the recording here, because that I think gets through the primary
I'll be back.
the primary setup.